So when I say colloquial, it's like one of those things where you've probably heard somebody say it before. Like, for example, objects in motion tend to stay in motion. That sound familiar to you? So colloquialism for the first law. The way I'd like you to know the first law is a little different than that. So I added the state of rest in there because I think you need to see it, but it's objects will maintain their state of motion or state of rest unless acted on by an external unbalanced net force. It's a fancier way of saying objects in motion tend to stay in motion, but I had to introduce the word force there because you need to have the word force in this rule. Force, give me a middle school definition of force or an elementary school definition of force. If I tell you to go force the door open, what are you going to go do?
Push
or pull. There we go. So all forces are just a push or a pull. There are hundreds of possible forces out there. They all come down to pushing or pulling. Now we're going to add to this, so leave some space between what you wrote down for the first law and what we're going to write down for the second law. Now, with only a few minutes to go, all of these have what I want to say. Yes, go ahead.
Can you, sorry, for the second law, can you define like inertia?
That's a good question. I'm really glad you did ask that because that's the whole goal of Monday.
Okay.
All right, so I will spend a lot of time trying to define inertia.
Okay.
But I will say this. If you can understand Monday's discussion about inertia, you will understand almost everything we do in here. Inertia is a seminal concept. It's what's called an intrinsic concept, an intrinsic property of matter. And although I don't want to launch into it too much, there are only a few intrinsic properties of nature. Only a few, a handful of intrinsic properties, things that are part of the fundamental nature of the universe, and inertia is one of them. And there aren't many. So when we talk about intrinsic properties, and the word intrinsic you probably don't have a definition for either. We'll define intrinsic too. But let's start here, because everybody's going to like this year. What symbol is that? I know, it's so funny when something becomes like a word. Like, because right now you guys are saying the word sigma all the time. And now, sigma is going to be a thing. But you know what the symbol means, right? What does it mean? Say it again. It means to sum. Newton's first law has something associated with it. You would call this an equation, and you'd be wrong. Okay? It's a set of instructions. The first law is telling you something to do. First, when you face a problem, one of the first things you're going to have to do is decide if you're looking at a first law problem or a second law problem. You have to decide. Now, the first law problem, it's clear what you're looking for. You're looking for an object whose velocity is constant, which could mean it's at rest, but it also could mean it's moving at 50 miles an hour as long as it's traveling in a straight line. So you put the cruise control on, point the car straight, go 50 down the highway, it applies. This rule would apply. Does everybody understand? What you have to note is the acceleration has to be 0. To apply the first law, the acceleration has to be 0. So that means the velocity is either constant or the object's at rest. Sigma means to sum. We're going to use a capital F as a generic representation of all the possible forces. We're going to put a bar on top because forces themselves are vectors. The first law says objects will maintain their state of motion unless acted on by an external unbalanced net force, which means in the first law, the forces are balanced. The state of motion is being maintained. That must mean this equals 0. Now, this is not an equation. This is a set of instructions. It says to add up all of the forces taking into account their direction. And setting them equal to 0. So if the first law is being invoked, if you think the problem is a first law problem, then you must add up all the forces that are acting on the object, take into account the direction of each of those forces, and set that equal to 0. That's how you apply the first law. Now, let's talk about the second law. There is no simple colloquial for the second law because most people just equate it to being a formula, which is inappropriate because none of these are formulas. So the second law, so again, if an object experiences an external, unbalanced net force, then the object's state of motion will change. It's going to accelerate. The amount of the acceleration depends on the object's inertia. When I use the word amount here, we're talking about how effective this force is at moving the object. So lots of objects experience forces, but how an object responds is the effectiveness. Now, there are 3 laws, but the first 2 laws deal with only one object at a time. You apply this to a single object. The third law is similar, except it's dealing with the unbalanced, and it tells you the same kinds of things. It says you are to add up all of the forces. Again, add up all of the forces, taking into account their direction. But this time, we don't set it equal to 0. It says this will cause an acceleration. The object will accelerate because of this. But how much it accelerates depends on the object's inertia. So although we get the acceleration here, what do you think M stands for? I know I said inertia, but why would we use M? That's right. When we talk about inertia, we are talking about mass, inertial mass. There's 2 kinds of mass. There's inertial mass and there's gravitational mass. Now, I can't impress upon you enough that you, in evaluating a problem, decide whether you believe that it's a first law problem or a second law problem. I'm going to say it very clearly. On Monday, we're going to have an advanced discussion about how we use these laws. Inertia will play a big role in that discussion. But the very first step of every problem will be to say, do I think this is a first law problem or a second law problem? If you can't tell, then you have to assume it's a second law. You default to second and see if the forces add up to be 0. That's what you do. Now, in all of this, the only thing Newton's laws can tell you, the only thing they can tell you, now they can tell you lots of things. I don't want to say they can't tell you other things. But when we apply the laws, they can tell you either one of 2 things. They can tell you either the size or direction of a force, or the size and direction of acceleration. This entire group of laws, this entire study, only tells you the A part of all those motion equations we talked about. So when we apply Newton's laws, we're either looking for a single force or we're looking for an acceleration. Now, you do understand those forces will be sometimes complicated, and maybe by finding the size of a force, we're finding something else, like how that force is being generated. But Newton's laws tell you a force or they tell you an acceleration. That's what they do. All right, we're going to end right there. A little different. And the third law is the one that all of you actually probably know, or at least you have a better colloquialism for. For every action, how does that continue? There's an equal and opposite reaction. Yeah, that's a colloquialism. How many of you have heard that colloquialism before? All right. So for every force, there's an equal but opposite reactive force. All forces exist in action-reaction pairs. Now, this brings me to something that I think you really need to kind of understand. This is how objects interact. All objects interact through force. That's how you exchange energy and momentum, is through force. But it's important to note that the first two laws just talk about what's happening to an individual object. This is the first time we bring in more than one object. And you don't see it there because it's not kind of obvious, but these two forces act on separate objects. So you're sitting in a chair right now. You are applying a force to the chair. Well, the reactive force is the fact that the chair is applying a force to you. Right? That force is keeping you from falling down, but you are pushing down on the chair. One of those forces acts on the chair, and one of those forces acts on you. They form an action-reaction pair. So there might be a dozen forces acting on you right now. Some of you are leaning on the table, twiddling your thumbs, the air is pushing in on you. There might be a lot of forces acting on you. But ultimately, for every one of those forces acting on you, there is a pair force acting on something else somewhere else in the universe. Which you might think sounds silly, but what's pulling you downwards right now? Well, that means that there is a reactive force of you pulling upwards on the earth. Now, the force of gravity acting downwards on you is a lot more effective than you pulling up on the earth. The force is the same, but let's face it, you're easier to move than the earth is. So your force on the earth is ineffective, while the force of the earth on you is very effective, right? You trip, I've watched you fall. It's entertaining, it's very effective. But the earth didn't move that much when you fell. You might think it does. Some of you think the earth revolves around you.